Hiya. Thanks for the great talk, Atta. And my name is Natalia Pryntsova. Thank you for joining me. I'm the team leader of Portfolio Enterprise Infrastructure team in Bloomberg. And today I would like to talk about services evolution required is forever. And you will see what I mean by it by the end of my talk. First, I would like to ask you a question. Please raise hand if you play any musical instrument. Oh, cool. Yeah, I can see the hands being raised. Cool. Yeah, thank you. Quite a big percentage, actually. Yes. I play as well, but even if you play or you don't play, you probably kind of heard about MIDI, right? MIDI is very popular, like format and protocol to kind of music instruments to talk to each other. And what kind of prompted me on the topic of compatibility is that I heard that MIDI didn't change since 1983. And initially I was like, well, why would it change, right? Music didn't change much since 1983. Music notation didn't change much since then. And the protocol itself is very straightforward. Like here I have an example of like middle C on channel 3 with certain velocity, and that's kind of not very difficult format. But then I've heard that MIDI is kind of have MIDI 2.0 in progress, and then it was released last December. Because also the music notation didn't change, the world kind of moved forward, right? The new instruments appeared with more precision, more capabilities, and MIDI had to issue a new version in the end. And one of the things which it's very praised on is that it's fully backward compatible with MIDI 1.0 because well, obviously there are so many instruments already out there, with this MIDI built in. So that kind of prompted me to think about compatibility a bit more, basically. And if you look at the definition like of backward compatibility, for example, on Wikipedia, it's quite generic, right? And in reality, we don't normally own like systems, products, and technologies. We own services and libraries and modules and databases and different kinds of APIs. So I've personally find like some mnemonics a bit more useful when kind of reasoning about compatibility. And the mnemonic for backward compatibility is new code should be able to deal with old data, which means, and it can be tested, right? You can spin up your like latest version of your service or your code. You can feed in previous version of your data into it, which is old data in this case, and you can see if it works or not, right? Forward compatibility mnemonic is the other way around. It's old code should be able to deal with the new data. And it's normally provided on kind of best effort basis, kind of we do our best. Why is that? Oh, I was trying to illustrate here why forward compatibility is on a best effort basis. In this picture, we have very simple kind of service and client, and they do like request response between them. Now, let's say if we own the service in this situation, and we just released the latest version of it. So the service is tagged as a new code. Then backward compatibility needs to happen here, whereas you see this yellow square. It needs to be backward compatible on request, right? That's where your new code deals with old data, which is current format of request. But the forward compatibility will happen on client side, right? That's why what we tagged as old code, which is basically just existing version of the client, should be able to deal with the new data coming potentially from the response. That's where the forward compatibility square sits. And that's why it's kind of a bit out of your hands, as far as forward compatibility is concerned, because you cannot force your client to do or not do anything. This is the theoretical view on compatibility. We have definitions and we have mnemonics, and we can draw diagrams, and kind of reason about compatibility. That's fine. In practice, what I found is that the actual compatibility is very heavily influenced by the serialization methods we use or the serializers we use. So to illustrate that, you can see like on the left-hand side here, it's schema resolution rules for Apache Aurora. On the right-hand side, it's updating the message type rules for protocol buffers. You don't need to read through them in detail, so just to show that they're quite long. They use slightly different language, and in general, they're quite extensive. And the practical compatibility is there is a theory of it, and there is this practical rules around compatibility. Also, what I want to say about compatibility in practice is that it's not a new problem, right? It exists for ages now, and we have a big variety of different serialization methods at our disposal now. But still, the challenge still exists. It's challenging to kind of evolve your API meaningfully while kind of keeping compatibility. And now I think this problem is actually more pronounced because we're moving from having like larger services into multiple smaller ones. So we basically have more APIs to manage. And kind of that's why the problem maybe becomes more pronounced now. What you may sometimes see with compatibility is a lot of growth by adding new optional fields. So here I have this get user requests. I put it in as like Python class just for illustration purposes, but you would see like, some very well-defined structure in the beginning. Some fields are optional, some are required, but after a certain timeline, it's like everything is optional because people don't want to break backward compatibility. And then you look at this massive class and you think, well, actually, some of those optional fields are not optional, and some of these required fields, we don't need them anymore, but there is no way to, make it nice and pretty. Sometimes the change is so big that there is kind of absolutely no way to maintain compatibility, and the new major version needs to be introduced. And introducing a new major version has big maintenance costs in general, because either you end up with multiple entry points to your service, and then every single entry point needs to be tested, supported, bugs needs to be fixed in it. Or you can say, okay, I'll cut my code completely. I will just have the instances running with the previous version. Then you still need to support this existing instances, right? And in reality, it takes months for your callers to migrate to the latest version. So major version is a big step, and it has a big maintenance cost. Then at all times, we need to be aware of these compatibility rules for our particular serialization method. So I wanted to have a look at a couple of them just to, to show what does it actually produce, right? Like what's going on there. First one I wanted to show is Apache Aurora. I wanted to show this one because it's quite unusual in a way. Apache Aurora has the concept of reader and writer schema. And by default, it actually kind of packs in the writer schema together with the data. So if we serialize this data token, like with two fields, A 127 and B is full, if we serialize it, by default, it actually packs in the whole schema in, and the only data token is this one underlined by red. Because like it's also possible to kind of to make it serialized data only, and in this case, it kind of assumes that the writer schema is known, and it doesn't use any field IDs or field types. So it's basically one data follows next data, follows next data. There is nothing in between. So if you look at this serialized data here, 6.6, 6F, 6F is full. 0.6 supposed to be the size of full, but it's why it's not 3? Well, we'll see it in a second. And this 2 bytes, FE01, it should be 127, right? But 127 is 7F. So why it's like, how does it get converted in the FE01? Raise your hand if you know, but but I'm gonna give a quick explanation anyway. So the let me see when you raise its hand. Okay. What majority of encoders do, they do thing called variant encoding. So it's the idea is that small numbers should take little space. If we don't do variant, then even, and we do like everything is in 64, for example, then even integers like 1, 2, 3 will take in 64, which is wasteful. So what variant does, it kind of reserves the first bit as a here marked in blue. It's like continuation bit, and then 0 means you are done with the current integer. 1 means read the next one, and then the rest of the integer is kind of split in 7-bit groups. Least significant first, most significant last, and that's how small integers take little space. If we do this magic with FE01, we will, but in kind of the other way around, we'll end up with 254. So 254, okay, that's fine, but it's still not 127, which what we would expect, right? So something else also happens, and it's called zigzag encoding. Zigzag has the same idea that small signed integers should take little space, because otherwise even like -1, -2 will be represented like a massive positive number, right? So -1 is 1, 1 is 2, 127 is 254. And that's how Avro, if you look at the output data, you can see this 127 becomes FE01 instead of 7F. Okay, that was Avro. Now, just to compare and contrast, what does Protobuf produce? Protobuf is more like, has a different approach a little bit, because it uses the field numbers, and it gives you like a pre-generated data classes to deal with the data. So here, you can see this underlined with blue is like a combo of field number plus as a type, and underlined with red as the data. And you can see foo is still foo, right? 66, 6F, 6F. 03 now it's not zigzagged, it's the size of foo. And 127 is converted into 7F, because Protobuf has a special sign type, so it doesn't need to zigzag every single kind of integer type it encounters. Now we looked a little bit at what Avro produces and what Protobuf produces, but you may say like, okay, what about our most kind of other most popular format, right? Which is JSON. What about just, I'm not going to bother with binary encoding and schemas and everything. I'm just going to use plain JSON and be happy with that. So the one thing I want to say about JSON is that the fact that we don't have a schema like written in a separate file doesn't mean that you don't have a schema. The schema is still there, it's just implied through code. So it's implied through the validations you do in your code. And I think the best thing to do with that is to make sure all these validations are in one place. So on the right-hand side, there is this validation middleware, which kind of a good way to group all the validators together. And then you have this one place where you define the format, define your kind of schema in a way. And there's still little gotchas with JSON parsers, because we know that JavaScript doesn't deal with big numbers very well. Like here, you can see it's cut. Or at the same time, standard Python JSON loader can deal with big numbers, no issues, right? So there's still a little bit of kind of things gotchas to be aware of in JSON as well. Now, if you use binary serialization or if you use JSON, there are a couple of approaches which kind of make our life a bit more easier when compatibility is concerned. For me, they both come from the tolerant reader pattern described by Martin Fowler. He says, only take the elements you need, ignore anything you don't. And to extend on it, also don't destroy anything you don't. They also known as must ignore and must forward patterns. And I put a small kind of 4 steps example to just kind of illustrate quickly. If we have 2 versions of the same schema, one only has field A, and version 2 has fields A and B. And on step 1, version 2 writes a data token, our favorite. A is 127, B is full. Version 1 reads this data. It can only read A, right, because it doesn't know anything about B. And here this must ignore pattern kicks in, right? It says, I don't know what B is, but I'm not going to crash. I'm just going to ignore it. That's must ignore approach. And then if it updates A, then the next method kind of kicks in. It says, oh, I don't know what this is B, but I'm not going to delete it from the data. I'm just going to leave it alone, basically, which is called also must forward B. Thanks to these 2 methods, right, when we read this data back in V2 in step 4, it is able to read updated A, 126, and whatever it's written into B. So the B value is preserved. I think these 2 methods are very useful to know about, and always check with your serializers, how do they behave in these 2 particular situations. They, like what is default behavior, what needs to be enabled by some separate setting. I would say there are some kind of situations when I would say don't ignore and forwards, which is like if you're checking a security token, I would probably say we shouldn't ignore and forward because there may be some issues with that. And finally, about required fields. So if we look at this serialized data, which we know very well by now, nothing in this data says this field is optional or required, right? It's totally enforced by the schema which we use to read this data. And so which may kind of prompted some thinking about, do we need required fields at all in our kind of serialization and schemas? On one hand, they communicate the intention. So like they say, this field is important, this field is not important. And you can avoid writing like more tests than you need, right? You can like offload some validation onto the serialization layer. At the same time, we make our life a bit easier now, but more difficult kind of in future, because like adding a required field to a request or removing a required field from response, for example, will break compatibility. And at the same time, they're not restrictive enough quite often. It can be extended, but it will make this elaborate compatibility rules even more kind of detailed in this case. And also like one question to think about is like, is removal of an optional field always backward compatible? In theory, yes, right? Because theory says, yeah, that's the whole point of optional field. In practice, I would always check what my particular serializer will do if I will remove particular optional field, especially if it's in the middle of something else. Also, from another practical angle, if you know this field is always has value historically, and you know your colors rely on it, right? You may remove it without breaking compatibility, but you're not going to remove it because you're going to break your colors. So from this perspective, also the kind of equal, required and optional fields. Personally, I kind of like, you probably know your use cases kind of best. So like I'll leave it to you to decide. Personally, I started to kind of not bothering much with required fields, like since after thinking about that. The kind of few takeaways from all this compatibility conversation really. For all APIs, a time for change comes sooner or later, and we should be ready. There are a lot different serializers around, but still it's challenging to maintain compatibility and evolve APIs at the same time. And what's actually defines compatibility is not some theory, but more the actual rules applicable by the to the serializer. And when you kind of thinking about API evolution, it's useful to remember about must ignore and must forward patterns. And it's worth kind of thinking about do I need required fields in my schema or not. With this, I would like to say thanks for listening. Yeah, if you, I will be in the lobby on the second floor after this talk. If you want to come and talk to me about serializers, compatibility, Bloomberg, or musical instruments you play, please come and have a chat. I'm up for it. Thank you.